What we're going to look at next is the idea of a line load. So you get just different distributed loads. So you get pressure, and that's a load spread over an area. You get a patch load, which might be a little, so you might have a floor. Let me just draw that. So you might have some kind of floor like that. And you might have a load that's just in the middle. That would be called a patch load. And so you'd have some kind of loading on that. But what we're going to look at in this course is mainly line loads. And so what we've looked at so far is all point loads. And so we've represented those by a line. And so you're just drawing a vector, basically. And the reason they're called point loads is because they'll be applied at a point. So you might have some loads. This might be a plank of wood or something. And you'd have a load on that. It's a point load. It's applied at a specific point. And so that's called a point load. Now, what would you use those for? Well, you might use them for something like a person standing there. And so that would be reasonable. So you've got some person standing there like that. And they might weigh 100 kilos. So they might weigh 100 kilos, about 1 kilonewton, something like that, 100 kilos if it's the same weight as me. And so you'd represent that person by a point load. But often in engineering problems, what happens is you end up with having a heap of point loads. And so you might have this, you might just not have one person on that. You might have, or at least you want to design it for the possibility that there could be a crowd of people on top of that. Okay, so we're wanting to design, this might be a bridge, in fact, rather than just a plank. So you're designing a timber bridge or something like that. When you're designing it, what you end up doing is you're designing it so that if it was completely crowded, it gets too much hassle to deal with all these individual forces. So what you do instead is you change those small forces into a uniform load or a line load. So what we do with that, let's just say we've got a bridge that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say that this is, I'm just trying to think how much space a person would take up. So they're probably going to take up about, say, 250 mils. So each, maybe 4 of them is a meter. 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. So this might be something like, so I'm just doing this very roughly. But suppose that bridge there was about 4 meters wide, say. And we assume that we can get 4 people per meter. And so every meter there's going to be 4 people. Rather than drawing all these individual point loads, what we'd say is, well, there's 4 people in a meter. Each of those people weighs 1 kilonewton. So we'd say, well, we'll just apply a line load of 4 kilonewtons per meter, 4 kilonewtons per meter, like so. So we've got 4 people, each of them weigh 1 kilonewton. You can get 4 of them in 1 meter. And so instead of applying all these point loads, we're just going to represent it by a line load of 4 kilonewtons per meter. So the way we draw that is we'd get rid of all these people. And there's a couple of ways people draw line loads. One of them is you draw little bumps like this. I have no idea why. That's how they draw it. It's like little semicircles. And then just above it, you'll write on the magnitude of that line load. So that line load represents 4 kilonewtons per meter. So if you were to take 1 meter long, what you'd say is, well, it's 4 kilonewtons per meter. So the equivalent, so that would be a total load on 1 meter of 4 times 1 would be 4 kilonewtons. Okay, if you were to think about how much load is on, a length of 2 meters, so say you take 2 meters instead. All right. If you've got a line load of 4 kilonewtons per meter, all you'd be saying is, well, it's 4 kilonewtons per meter, 2 meters. So the total load on a 2 meter length would be 8 kilonewtons. And so that's basically why we use line loads. Now, there's another way we can think about these different line loads. Now, it doesn't have to be that it's a constant line load. It can vary. So to think about that, it's maybe one way of thinking about it is just to think about stacking bricks. So let me just delete this, and I'll drag these across, or we'll just come across here, and I might shrink this down a little bit. So what we've got here is a bunch of bricks. Let's assume that these bricks are 200 millimeters wide. So they're 200 mil wide, or 200 mil long is more realistic actually. And let's say they weigh 20 newtons each. So to get a meter, we'd stack 5 of these together. 1, 2, 3, 4, 5. So you'd stack 5 of those. The total weight would be 5 times 20. It would be 100 newtons. And so the equivalent line load, so that was one way of drawing a line load. Let me just say this before I go on. Another way of drawing a line load is to draw a straight line across the top and then just draw some little arrows down every now and then. And that's just another way of drawing a line load. Let's go back to the bricks. So you got 5 of these bricks would cover a meter. They would have a length of 1 meter because they're all 200 long. They weigh 20 newtons each. So in total, they weigh 100 newtons. So the equivalent line load would be 100 newtons per meter. Now there's another way to think about this. If you've just got that little brick that's 200 wide, so that's the same as 0.2 meters. And so you could just say, well, each one weighs 20 newtons, divide it by 0.2 meters. So the equivalent line load would be 100 newtons per meter. Okay, it's just getting to the same answer, just by different ways. So you're always thinking about the load or load divided by length gives you that line load, the magnitude of the line load. Okay, so like I say, so if you've got just one layer of bricks all stacked along, the way you would represent that is 100 newtons per meter. So if you did 3 layers of bricks, so you got 3 times the load, so each of these would be 60 newtons, 0.2 wide, 60 divided by 0.2 would be 300 newtons per meter, or you could figure out how 1, 2, 3, 4, 5, they're 200 long, so you could add up all these bricks, figure out how many bricks fit on a meter, and you would divide, or that load would be equal to the line load per meter. Just a little mistake there, I'll fix. It should be 300 newtons per meter. And so these bricks, you would represent those as a line load, and you would just draw the same thing, draw a line. I'll mostly use this way of doing it. It's a bit more precise than just drawing the little bumps for a UDL universe. And a UDL, I should point that out. Oh. UDL is what's called a uniformly distributed load. Okay, so it just means that it's constant. So if we had 1 brick, 100 newtons per meter, we figured that out up here. 3 bricks, you'd have 300 newtons per meter, but it doesn't have to be uniformly distributed. You could have more bricks at one side and less on the other. And so in here we've got 4 stacked up. So across at this end, this isn't exact, but it gives you an idea. And so you've got 4 bricks at this end, each of them 20 newtons. So we've got 40 newtons. How much have we got? 40 newtons. 80 newtons, sorry. And then you divide that by the width of the bricks, 0.2. So it's about 400 newtons per meter at this end. The other end, we're down to 0 newtons per meter at the other end. And so to roughly represent these bricks as a line load, you'd end up drawing a triangle, basically. 400 newtons per meter at one end, because you've got 4 bricks stacked up, down to 0 newtons per meter at the other end. And this you call a triangular load. So you've got a triangular load like that. Now, the total load here would be 1, 2, 3, 4, plus 3, 7, 9, 10. Let me just check that again. Might not quite work, but it might. Let's just figure it out. So we've got 4 plus 3, 7, plus another 3, 10. So the total load there would be 10 times, each of them weighed 20 newtons. So that would be 200 newtons. Now, this is 1 meter long, say. So what we can do here is we can take this line load and we can figure out the area of this. So it's a triangle. It's got a height of 400 newtons per meter, and it's got a base length of 1 meter. Have to make sure that the unit here is the same as the length unit you're working in. So this is per meter. This is 1 meter long. So that's 1 metre. Now if we figure out the area of that, and so the area of that would be half, so it's a triangle, half times base times height, so it's a half times 1 metre, this is 1 metre, times the height is 400 newtons per metre. I'm just putting the units in here just so we can see what's going on. And what we're going to end up with, the units of meters will cancel out, you're just going to end up with newtons, and so that would be 200 newtons, which is the same as when we added up the weights of all these bricks. Let's just go back and check that again for these ones here. So we've got 300 newtons per metre, that's 2 metres long, so this is 2 metres. So first of all, let's calculate the area of under that UDL. So it's 300 newtons per metre, that's essentially the height. It's a rectangle, this is 2 metres long. And what we call, and then so what we're going to get is, call it total load maybe. Total load, and we'll calculate it the two different ways. Let's do it by the area first. So for this one, the load is equal to 300 times 2, which equals 600. We're in newtons, just checking. These units of length are the same as the units of length in this, so that'll work out okay. So 600 newtons. Now, let's just have a look at the bricks. So we've got 3, now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 long, that makes sense. So we've got 10 bricks along the way, 3 bricks high. So we've got 30 bricks all together. So we've got 30, each of them weighs 20 newtons. 30 times 20 is 600 newtons. So what we're seeing here, I won't do it for all of them, but what we're seeing here is that if you want to calculate the total load that you get from a line load, what you do is you just treat it like a shape and you find the area. So you multiply the height, which is basically the magnitude of the line load, and you multiply that by the length of the line load, and that will give you the total load. So it's just like calculating the area of that shape that you've made by drawing the line load, and it still works if it's triangular. And you can do this yourselves if you want, you can show that it's still true if you're looking at something trapezoidal like this. Okay, so this type of line load, you can see it's almost like you've got a triangle on top of a rectangle. And if you figured out the area of this, just taking these values as height and using your width, you'd find that the area under that line load would be the same as the total mass of all these bricks added together that it's representing. So the total load from a UDL is just equal to the area under the total load from a line load. It's not really a UDL because it's varying. The total load under a line load is just equal to the area of the shape, as long as you make sure the units for the line load, say 400 newtons per meter, is the same as the units you're using for your length. That'll work out okay. Okay, so that's the basics of what line loads are. Just think about that again. So you're using line loads in engineering because you've got too many point loads, so you just spread them all out to make them into a line load like this. If you want to think about what they really mean, just think about stacking bricks. It'll give you an idea of what it means. So if you've got a high line load, it's like you've got a lot of bricks on one end and you've got down to 0 at the other end. So that means you've got no bricks at the other end. That's the way to kind of visualize them. And then if you want to find the total load under a line load, you just calculate the area of the shape it makes. And we'll also find a little bit more in the next section about where that load, so if you were to take this and change it into just a single load, so a single point load, instead of having this, we need to figure out where we would put that so that it wouldn't change anything as far as these supports are concerned. So we'll talk about that next.